Thank you, Erica, for having me. Super excited to be here. Um, this is my first time in Seoul, so love the city so far. How's everyone's day so far? Okay, good. Let's get some energy in the room. Yeah? So my talk today is titled Power of ZK Beyond zkEVMs. And so my assumption is, I think most people are familiar with zkEVMs, but let's talk about other approaches to leveraging this powerful technology that is ZK. And so I'll shed some light on these other approaches, what are some benefits, and use cases of these approaches. But before that, a little bit about myself. My name is Manasi Vora. I'm a VP of product growth at this company called Risczero, where we are building this general purpose zero knowledge virtual machine, which I'll talk about in a bit. I just joined the team 4 months ago, so relatively new to ZK, but I've been in the crypto space since 2017, done a lot of different things, but previously was building a decentralized data storage protocol at Science, kind of maybe some of you are familiar with it. So with that, let's dive into zero knowledge proofs. How many, I know Anthony asked this question, but how many of you are familiar with the concept of zkBs? Quite a few? Good, okay. I think I'll do a quick demo to demonstrate, just this core concept. It's super simple. I need one volunteer if anyone wants to step up. Fun up, if no one's stepping up. Or I can go. So what I'm going to do is I'm going to prove to all of you, but specifically to Pranav, that I know this is my phone, and then I know the passcode of this phone without revealing the passcode. That's one way to tell you, just by telling you the passcode, but without revealing the passcode, I'm going to prove that this is my phone. So Pranav, just put a message in here, don't show it to me, and then lock the phone. Thank you for being a volunteer. Okay, so if I didn't know the password, I wouldn't know the message, but because I know the password, I love this message. Hi, Mom. Is that correct? Yes. Okay, and he verified it. So, thank you, Pranav. But this is essentially a very simple example where I proved something to you, a statement that's true, without revealing any additional underlying information. And so that's what zkBs are. zkBs are these cryptographic proofs to prove something. And there are two key functionalities that zkBs enable. One is privacy, which Anthony talked about. And in this context, I preserve the privacy of my phone. I did not reveal the password. And the other functionality that zkBs enable is verifiable computation. And this is what I'm going to focus a lot on. Anthony already covered a lot of the privacy applications, so it makes my job easier. So what is verifiable computation? Verifiable computation is essentially your ability to verify a certain computation was done correctly without having to rerun it. So again, in this example, I was the prover, Pranav is the verifier. And say, now Pranav wants to offload certain piece of computation. He doesn't have the hardware or doesn't have the time, and he's like, Mansi, hey, can you run this code for me and give me the outputs? It's like, sure, I can run this piece of code and give the outputs of that code to Pranav. Now, Pranav has two options. He just has to trust me blindly that I ran that code correctly, did not have any malicious intent, and gave the output. So he's either trusting me blindly, or he has to rerun that computation on his own and check the outputs and match the outputs results, which seems wasteful, right? Why would you rerun the entire computation? So that's where zkBs come into picture, where when I'm running this piece of code, I can also generate a zero-knowledge proof that I ran that piece of code accurately. And then the only thing I have to give Pranav is the zero-knowledge proof and the outputs. And now Pranav doesn't have to trust me. He can verify this zkP and use the outputs if the zkP is valid. So there's a functionality for zkP, which is essentially verifying the zero-knowledge proof is significantly less work than having to do the computation again. And so that's kind of what verifiable computation enables, is this offloading of computation in a trustless manner. Any questions so far? Okay, I think everyone's kind of on the same page. Great. And so extending that verifiable computation functionality, that brings us to scaling in the Ethereum context. So right now what happens, assume that's ETH layer 1. All the transactions, all the computation that happens on Ethereum is essentially run by all nodes again and again. Each node is running the entire chain, verifying every single transaction, and doing a lot of extra work at the moment, and also causing just scalability bottleneck. And so as we determined earlier, that's kind of wasteful, and what you can do is you can leverage or offload that computation on-chain. So zk rollups essentially bundle these transactions that are happening on-chain, and they will take it off-chain, do the execution, and submit a validity proof that the execution was done correctly. So you can offload all of this heavy computation. You don't have to worry about it. You don't have to do it on-chain. And you can transfer that off-chain, but you still know that it was done correctly, and you don't have to blindly trust the computation. And so essentially, zkEVMs are zk rollups, but in the EVM compatibility context. Any questions? Yeah, validity proof is essentially a zk proof that proves the entire transaction was done correctly from the initial state to the final state. Good question. Okay, you're all zk experts now. Let's go. All right, so this is kind of the crux of my talk. zk is a very powerful technology that we can leverage in various kinds of decentralized applications, from privacy-preserving one to just complex, computationally heavy applications. And zkEVMs is definitely one way of doing that, but there are so many other approaches to leveraging this technology. And zkEVMs are specifically optimizing for EVM compatibility, whereas these other approaches are building the technology with zk-first design in mind, and that enables them to harness its full power of zk. And so that's super exciting. Let's look at some of these approaches. I mean, you're already familiar with Elio because of Anthony, but let's start with the first approach. This approach is, go hardcore. You can design and write zk circuits on your own, which is definitely doable. As you're building your application, you will design these arithmetic circuits and leverage the zkP generated through these circuits in your application. It's also incredibly hard. You need to understand the zk cryptography. You need to understand the math behind it. It just takes a lot of time and effort if you're building a simple application. The other approach is using or building on a zk-enabled L1. So now there are L1s in the market that are built with zk-first mentality, and you can build your applications using those L1s, and you will get all the benefits of using zk in that manner. I think the kind of trade-off is these L1s, as we know, are really hard to bootstrap. You have to create an entire new ecosystem around that. They also have new languages that developers have to get comfortable with. This is where zkVM, or zero-knowledge virtual machines, come into play. And when I say zkVM, I mean general purpose. So when we talk about zkEVM, you drop the E. zkEVM is, again, like I said, EVM compatible, specifically designed to run smart contracts or things that can be run in an EVM context, versus zkVM is a virtual machine that allows you to run software that can be run on your computer. Any software that can be run on this laptop, on your phone, you can run that software in the zkVM and generate a zero-knowledge proof. And so it just broadens the application space and uses zkP for very general purpose use cases. Even in this zkVM context, there are two approaches. One, Kairos, Starknet, maybe people are familiar with it. the first approach is, again, creating a new language, a custom language that's, domain-specific language. That's what DSLs are. And those are created to leverage, that particular zkVM. It's like specific to it, which is great because you're using a very specific language that can harness the power of zk. But again, like I mentioned, whenever there's a new language created, one, there's a little bit of barrier to entry. Devs have to learn that language. Not only that, you have to build all the tooling and the libraries and all of the pieces for that language from the ground up. And that's a difficult job to do. It can be done, but it takes a lot of resources. And so that brings us to this other approach of zkVM, which is what Risczero, the company I work for, is taking. And that's targeting existing languages. The architecture that we've taken here is essentially enables us to target languages like Rust, C++, Go, traditional languages that devs are familiar with, that have existed for years. You can leverage the cargoes and libraries written in this language to build your applications, and you can still use the power of zk. So in this context, you're focused on building, as a developer, you're building your, you're solving a problem for the end user, you're focused on building your application. You don't really have to worry too much about the underlying zk and still plug and play zk into your application. I want to give an example of how this works. Are people familiar with Overcooked? No? Oh my God. Okay. It's my all-time favorite co-op game. Check it out if you haven't played. It's on PS4, it's on Xbox, I think Switch as well. I thought more people would know Overcooked, damn it. Anyway, now you will know. So this is my favorite game in the Web2 world. And if you're not familiar, essentially you are a chef in this game. And you have so many different responsibilities. And your goal is to, cook meals and serve customers. And in that process, you have to cut vegetables, you have to cook meat, you have to assemble all the order, you have to wash dishes, you have to deliver product, you have to coordinate with your friends. A lot of fun, but also a lot of different work. And if you're better than me, you wouldn't reach this stage. But in most cases, sometimes you end up burning your kitchen because there's like compute overload. You're like doing so many things, it's exhausting. So going back, I think you can think of, say, in this like Overcooked example, the chef as EVM, or the chef as like this person who has a lot of responsibility, has a lot of tasks, and you're maybe a friend who is joining you in the Overcooked game as a sous chef. And sous chefs are really good at specialized things. They'll do this one thing, but they will do it really well. And so, say, a sous chef is really good at cutting vegetables. And so what you can do is offload that responsibility to the sous chef. You don't have to worry about it, and you can focus, and you're freed up to do other things. And so when you think about zkVMs, the general purpose zkVMs that I'm talking about, you can think of them as similarly the sous chef in this context, or co-processor. And so, the EVM is your central processing unit. You are using it to do smart contracts, your security, your consensus. And then you can leverage the zkVM as a co-processor to do really heavy, computationally heavy things that is prohibitively expensive because of gas cost on-chain. And that's kind of the example here with the co-processor. All right. Hopefully, everyone is excited about zkVMs now, but I'm sure everyone's like, okay, how does this actually work? Okay, let's get into the details. I'm going to showcase the example of zkVM with this product that we are launching called Bonsai. Bonsai leverages the RISC-V zkVM that we've built, and it's essentially enabling developers to build general purpose, truly general purpose applications using zk compute, both on-chain and off-chain. So that the off-chain part, I won't talk a lot about that, but that's equally important because, the use cases of zk are not just in crypto. There's so many Web2 applications that can leverage zk technology, and that is also something Bonsai can enable. But let's get into the fun part. So in this example, blockchain, let's assume this is your ETH L1, and Bonsai is this like co-processor zkEVM. And so on your ETH L1, you'll, in the same manner, you'll write your smart contract, you'll create your application and deploy it. And from that smart contract, what you'll do is any heavy computation that's like really not, optimizable from a gas standpoint, you'll ask Bonsai, this is kind of the Bonsai proxy or relay contract. You'll ping it and you'll ask it, hey, I don't want to run this computation. I'll give it to you. Can you run it in a zk context and bring it back to me? So that's what the ping is happening. This is all on-chain. The second contract is also a smart contract on-chain. Now this contract essentially sends it to the Bonsai kind of proving marketplace, where the proof is added to a request pool. I won't go too much into the details around the marketplace, but essentially in the background what's happening is there's a lot of provers who are bidding for your request, and these provers will, one of them will pick your request, run it in the zkEVM, and the prover is doing all the infrastructure that's needed, all the coding that's needed to run the zkEVM, and taking all of that work from you. And it'll run this program and then generate what we call receipt, which is essentially what I explained as proofs. So the zkEVM receipt is generated. This is all happening in the Bonsai context. And once that receipt is generated, of course, we can deploy that receipt or send that receipt back on chain as is, if you want. But usually, again, you don't want to post every single request, every single proof on chain, because that's, again, going to bloat up the chain. So this concept of recursion is super powerful in crypto. And again, don't have too much time to go into it. But essentially, you can combine a lot of different proofs across your application, across other applications, into a single proof, single root proof, that then can be, again, using this like relay bridge contract, submitted back on chain. And so what this bridge contract does is also handles the verification part, which is what Pranav did. In this case, it'll verify the proof that was submitted by the Bonsai network for you, and it'll do the verification, it'll make sure, yeah, this looks correct, the computation was run correctly, and then send the final output, which is what you need, essentially. You need the execution to run, and then you need the final output. Send that back to your contract. And that's kind of how you can think of the Bonsai zkEVM as a co-processor expanding the capability of on-chain contracts. Okay, if you're interested in learning more about Bonsai, I definitely recommend taking this QR code. Love it when all phones go up. I love to see that. Okay, let's move on. So what are some benefits of this? Like I said, using zk, you can use zk in so many different approaches, zkEVMs as an L1. What are some benefits that you get just by using it as a general purpose zero-knowledge virtual machine? First of all, we already spoke a lot about offloading compute. This is when, the computation on chain can be very expensive. We all know gas cost is like super expensive. With Ethereum, you can only do minimal computation on chain. And so you want to build really complex real-world applications. What you can do is offload the computation, and this provides scalability on your base layer, which can be Ethereum or any chain. The second thing it enables is smart contract complexity, which is, again, like I mentioned, with Ethereum and EVM generally and Solidity in particular, there are just certain constraints in the way it was built. It was built very optimized for EVM-specific transactions. And so the ability for your smart contract to do like real-world applications, really complex applications, is limited by this constraint. And so if you use a zkEVM as a co-processor, you're not constrained anymore, because now you're writing program in Rust, C++, Go, these languages that are general purpose, and you can express a lot more in that format and still leverage all of that expressibility in these languages with an on-chain contract. I think this is a big benefit, leveraging existing languages. It's a benefit both for Web3 devs, but also Web2 devs who are not familiar with Solidity, who have to learn all of that language. They don't need to learn all of that. They can use their knowledge in Rust, C++, Go, and use the tooling and libraries that exist. So if I give an example, if you're building a on-chain game, in a lot of cases, you have to build the tools, build the libraries, build the different pieces of an on-chain game, as well as build the game itself. If you're using an existing language, the benefits are there's so many open source libraries out there. You can just plug and play. You can leverage, call this particular library, and then build your application in a very limited, low time to development manner, which is you can build it faster than in other application environments. And I think one other thing I want to point out is, languages like Rust have been around for many years, and they've been battle tested. They have done security research and reviews of these languages. And so compared to any new language that will get created, these languages that have existed are going to have a lot more security guarantees in place. And so I think we've seen some hacks in the crypto space, and hopefully that'll change over a period of time, but leveraging existing languages definitely bridges that gap. Finally, I think this is more specific to Bonsai's benefits, where you're writing this off-chain logic. It's in a chain-agnostic manner. So, for example, you are building an application that needs to work on Ethereum and Solana. Now, in the current environment, you'll write a Solana code and an Ethereum code, and then have figure out a way for those to communicate. Versus here, you're putting very minimal, a small smart contract on each chain, and most of your code that you're writing is written in this common language, Rust, for example. And so that code that you've written can be deployed everywhere. You don't have to rewrite that code for each chain if you're building a multi-chain application. And then finally, the multi-chain support piece is also important. Like I said, let me go back to this. This proof that gets generated and rolled up can, of course, go back to the chain that you requested it from. But the proof can also be submitted anywhere. It really doesn't matter. It can be submitted on other chains. It can be just, you can have a Web2 API call for those proofs. And you can access that proof from any environment. So essentially, the multi-chain support comes out of the box. OK, let's talk a little bit about use cases. Let's make this real. What is being built in this zkEVM context? How are people using it today? So these examples that I'm going to give, they're actual applications that devs have built on the zkEVM as of now. The first category, again, I'm going to continue hammering the fact that you can use it for off-chain compute. Let's talk about a club. Are people familiar with the club? No? OK. Club is just essentially a central limit order book, which is the way how traditional exchanges, there's a buy order, there's a sell order, there's an order book, which there's a matching algorithm that does the matching, and that's how trades happen. Right now, it's extremely computationally expensive to do a matching algorithm on-chain. I don't even know how many thousands of dollars you would have to spend just for matching one trade. And so what you can do is push your matching algorithm off-chain and on Bonsai, keep your just basic kind of smart contract functionality on-chain where you accept these orders, ping Bonsai, ask it to run the matching algorithm. It'll do the matching and submit kind of the match trades that can be settled back on-chain. So it's essentially expanding what DeFi can do. Right now, we have a lot of DeFi applications, but they're not really representative of TradFi DeFi applications. They're not as complex. You don't have all the functionalities. You can't run Black-Scholes options pricing model on-chain because it's just not computationally feasible. And so expanding the capability with this off-chain compute is super interesting use case. I think it's the same with gaming. Again, your gaming logic, put that on chain, good luck. Your gaming engine, putting that on chain is going to be really hard. And so what you can do is essentially, again, offload all of that compute and create really, like right now, the games that exist in crypto are very primitive. And so I think with this, you can really start building games that exist in the Web 2 space, something equivalent to that. I think this is the part. I'm not going to talk as much about privacy applications, but there's this like hidden secret component, which also enables a lot of use cases. The first one is a zk proof of exploit. So this is a way for white hackers to coordinate vulnerabilities in applications with the team. So either you can just tell the team that, hey, I found a hack, they believe you or they don't, and it's a long process for you to just go back and forth. Instead, what you can do is find this vulnerability and create a zero-knowledge proof of the vulnerability that shows that something is wrong with the smart contract or whatever application you're trying to find a vulnerability or hack around, and submit that proof. And when you do that, the team can actually verify that there is actually something wrong with the application without getting to know what the exact exploit is. And so they're still incentivized to work with you and learn, okay, yes, we agree that there's something wrong. Let's work with you. And we'll pay you. Let us know what the exploit is. So that's kind of the hidden secret, or like hiding a piece of information, but also still being able to prove that a statement is true. The other application in the same kind of context is proof of assets. A lot of centralized exchanges don't reveal how many assets they are actually holding. They, or they have these like audit firms who audit their balance sheet, and we have to trust that that's all done correctly. In the zk context, they can send you a proof that they're actually holding those assets without revealing any of their wallet information, which has like privacy implications. This is another use case that I'm super excited about. This is kind of merging the world of optimistic rollup and zk rollup. So in the optimistic rollup world, the way it works is you just assume that these transactions that you're pushing off-chain are done correctly. And then there's a 7-day withdrawal period, which is where you do these like fraud dispute mechanisms. And if a fraud is detected, you would essentially rerun the entire computation, the transaction on chain, to make sure, okay, was the fraud correct, not correct, and based on that, that's how optimistic rollups work. Now, if you use zk in an optimistic manner, so you're still doing all of the transactions in an optimistic manner, but if there's a fraud that gets detected, you use zk proofs. And that just reduces the window from like 7 days to a couple hours, and you can withdraw your assets much faster than what's possible right now with optimistic rollups. And I'm really excited because I don't know if you've seen, Optimism has actually put out an RFP to build a zk fraud proof in their optimistic rollup. And of course, the last use case is you can build zk rollups using the zkEVM. So you can build a zkEVM using the zkEVM, because it's a general purpose technology. You can actually use zkEVM, zk Solana, zk, whichever application chain, whichever blockchain you want to leverage, you can build a rollup for that chain. You can also deploy your application as a rollup, which is a really new concept, but it's fascinating that you can actually deploy your entire application just as a rollup and then connect it to any chain. Okay, last slide, conclusion. I think the potential for zk is really massive. There's a lot. These examples, use cases are just scratching the surface of what's possible with zk. It all started especially like in the crypto context with zkEVMs, but zkEVMs are up and coming. And there's just the design space of leveraging zk is multifaceted. Each, of course, approach has its own trade-offs. But there's a lot of potential to make zk tech accessible to a point where you don't have to think about what the cryptography is, and you can still leverage the technology in your application. And so specifically with Risczero, we are targeting existing languages and enabling this like new wave of decentralized applications. And one thing I'll leave you with is, if you're not paying attention to zk, you should. This is definitely, I believe it's the future. Thank you.